So Ullmann's theorem is a fundamental theorem in quantum information theory. It's fundamental because it answers precisely this question, which is, when is it the case that two pure states can be mapped from the one to the other by acting only on parts of the state? So these are bipartite states, and I want to know when can I map the one to the other by acting only on one of the two systems on which the state is defined. And Ullmann's theorem gives the answer to that question. So let's see how it goes. Let's first start by reviewing what we saw about purifications. So starting from a density matrix ρA, I can purify it in the following form, and one possible purification for this matrix would be root 1/3, 0 on the A system, and then I could put an arbitrary label for the B system. Let's put a 1 here for B, plus root 2/3, 1, and then let's have a 2 for B. So this 1 and 2 that I introduced here, this is an arbitrary basis for an arbitrary system B that I'm creating in order to define the purification. I could have given you a different purification of the same density matrix, state psi prime AB, could have defined as root 1/3, 0 on A, and maybe if I feel fancy today, I'll use the Hadamard basis plus B, and then root 2/3, 1, put a minus on system B. So these are two different states, they're orthogonal, but they're two purifications of the same state. They have the same reduced density on system A. And what you can see about them is that the only change I made is that I used a different basis for B, so I can define a unitary which acts only on the B system and would map the 1 state to the plus state and the 2 state to the minus state on B. This is a unitary transformation such that if I consider the identity on A tensored this unitary on B, and I apply this to psi AB, then I recover psi prime AB. So this is the freedom that you have in choosing a purification of a given state. There's always at least a certain unitary degree of freedom on the B system. Now, is that the only freedom that you have? And Ullmann's theorem gives us the answer. So here is a statement of the theorem. Ullmann's theorem says that any two purification, psi and phi, of the same reduced density on A must be related by a unitary on the B system. Now let's immediately see why this answers the question that I raised at the start of the module. Suppose that we have these two states, and I can draw them like this. I have a system A, I have a system B, and a state psi AB that maybe is entangled between A and B. And now I have a copy of system A, copy of system B, and another state, psi prime AB. And the question is, when is it the case that you can apply a unitary on the B system only, act by the identity on A in a way that maps the state to the other? Well, a necessary condition is that the reduced density on A are the same for both states. So here I should have a reduced density ρA, here I should have a reduced density ρA, because acting by a unitary on system B is not going to change the reduced density on A. And Ullmann's theorem says that not only this is a necessary condition, but it's a sufficient condition. If the two states have the same reduced density on A, then they are two purifications of the same state, and the theorem says that they should be related by a unitary. So this is a very powerful theorem. Let's give a proof. How do we prove this? Well, let's use one of our newest tools, which is the Schmidt decomposition. So to get started, we have a bipartite system. It's natural to write the Schmidt decomposition of the associated states. Let's do it. So for psi, in general, I can write it as sum over I, lambda I, ui, Schmidt vectors for system A, vi, Schmidt vectors for system B. Similarly, phi AB, I could write as sum over I of some other coefficients, maybe mu I, and then I would have wi on system A and zi on system B. Now we saw that there's sometimes a little bit of freedom in the choice of the Schmidt decomposition, but not much. In particular, we can infer a lot about these coefficients and vectors by looking at the reduced density. So if I take the reduced density of the state psi on A, I would get ρA that is going to be equal to the sum over I of lambda I squared ui, and ρB, which is equal to the sum over I of mu I squared wi. And because both the ui's and the wi's are bases of system A, these lambda I squared and mu I squared, they're uniquely defined as the singular values, sorry, this should have been a rho A, as the singular value of the same reduced density matrix rho A, because that's the assumption of my theorem, which means that necessarily lambda i's are equal to mu i's. So in this decomposition, it should be the case that we have equality here. Also, the Schmidt vectors we saw are not uniquely defined, but what freedom do we have? There's two things. One is that we have a freedom in the phase, but let's imagine that I choose the phases to be the same. If necessary, I'll just change the phase of vi or zi to accommodate for that. And also, I can assume that the vectors are the same. The only freedom I have is when there's a degeneracy in the spectrum of the reduced density matrix, and in that case, I can choose any basis for the eigenspace that's associated to that degenerate singular value. So I can use the same basis for the eigenspace both for psi and phi because they have the same reduced density. And so again, I can ensure in this way that the wi's are equal to the vi's. So here is what I can always write my Schmidt decompositions like. And now the only remaining part is the part on the B system. And these need not be the same because I don't know that the reduced densities on B are the same or not. They might be different. What is the case though is that this is a basis and this is a basis, which means that there is a unitary map, UB, that changes the one basis in the other. I can simply define UB to be the unitary operation that maps each VI to ZI on the B system, and then U does exactly what we want, meaning if we act as the identity on A and as U on B, this is going to map our first state psi AB to the state phi AB. So not only does Ullmann's theorem say that this unitary on B only should exist when the states have the same reduced density, it also gives us a prescription for finding what the unitary matrix is. We simply have to write the Schmidt decompositions of psi and phi. Because they have the same reduced density on A, we know that we can choose such decompositions that are such that the Schmidt coefficients are the same and the Schmidt bases for the A system are the same, and then the unitary UB will simply be a unitary that maps the Schmidt bases for the B system associated to the second state.